Well, let's take a look at some chemical reactions of these alkenes. Much more interesting, much more reactive compounds than their alkane counterparts because of this carbon-carbon double bond, which is a bond of higher energy and a bond that's much more susceptible to breaking when molecules collide. So what we're going to look at is a succession of these addition reactions. Where another incoming molecule, like a hydrogen halide, hydrogen bromide in this case, smashes into that double bond, and that double bond breaks open. Bond breaks open, giving us an orbital on each of the two carbons, and those two orbitals grab a new chemical partner. So we add the molecule across the double bond. One of the carbons grabs the hydrogen, one of the carbons grabs the bromine. So we say that we have an addition reaction across where that carbon-to-carbon double bond used to be. Now the reaction follows what we sometimes refer to as Markovnikov's rule. When we have an unsymmetrical alkene, which means that we've got different bits on the side of the double bond, when a compound like this is adding to the alkene, this hydrogen halide, one carbon gets a hydrogen, one carbon gets a bromine. The Russian scientist Markovnikov realized that when we look at the initial alkene, the side which has more hydrogen at the beginning of the reaction is the carbon which gets the hydrogen being added. So the carbon with less hydrogen is the one that gets the halogen. If we look at a molecule here, here's carbon 1, carbon 2, and carbon 3. Carbon 1 here, to make up a octet, we have two hydrogens which have been omitted. From this point here, 1, 2, 3 chemical bonds, there's only one hydrogen attached to this atom. So with more hydrogen here, this is the side that grabs the hydrogen. We can show that now, the hydrogen which has been added, bromine to the other one, because there's the other two hydrogens which would normally emit. This is Markovnikov's rule. The rich get richer. The initial carbon in the double bond which already had more hydrogen is the side to which the hydrogen adds in the chemical reaction. Therefore, the other carbon with less hydrogen is the one that gets the halogen atom. Second reaction. Again, look at the two carbons in that initial double bond. In this position, with 1, 2, 3, 4 bonds coming from that point, there's no hydrogen attached. The atom already has an octet. From this position, with 1, 2, 3 bonds, there is one hydrogen here. Adding on HCl this time, the hydrogen adds here, and the Cl adds to the opposite side. Addition reactions will be add that molecule, that attacking molecule, across the double bond. Likewise for this reaction here. We draw the product, draw that initial skeleton product. The basic skeletal framework is still there. As we look at the hydrogen fluoride, which is going to add from this position, 1, 2, 3, 4 bonds, there isn't any hydrogen at this point. From this point of the molecule, 1, 2, 3 bonds, make the octet, there is one hydrogen applied from this position. So this is the side that's going to get the hydrogen, this is the side that's going to get the fluorine. With the addition of the fluorine, the addition of the hydrogen. You can either just show the hydrogen that's attaching, or show both, or just leave it blank, and just leave it as a simple line item formula. without those hydrogens there, the implication is that that position now does have two hydrogens. The double bond is gone. So these are what we refer to as addition reactions of hydrogen halide compounds. We look at the molecule, and if it's unsymmetrical, there's different carbon branchings on either side of the double bond. The side which has more hydrogen originally is the side which is going to get the hydrogen in the addition. And the side with less hydrogen is the side which is going to get the halogen. General one So let me just quickly draw in the answers. Gosh, that was really fast. So again, looking at initial molecules, there's where the reaction is going to occur. It's the alkene bond, which is wrapping up all the activity. This side with 4 chemical bonds, there's 0 hydrogen. With 3 chemical bonds on this side, there's 1 hydrogen. Alkene rule, the side which has more hydrogen is the side that gets the hydrogen. So we can either show that hydrogen addition or just leave it blank. The implication is with 2 bonds, if that's blank, is it was now 2 hydrogens instead of 1. Now on the other side of the double bond is where the halogen, the chlorine atom adds. That's the only change. It's just attachment across that forward double bond. This time, 1 hydrogen at this position, but 2 hydrogens at this position. So the hydrogen adds on to the end, and the fluorine adds on to the inner carbon. Hydrogen iodide, 0 hydrogens here, 1 hydrogen there. We know because it's the octet rule, 4 bonds, 2 electrons in each bond to make this octet. So 1, 2, 3 bonds, and there's an emitting carbon to hydrogen bond. So the carbon rule says the rich get richer. That's the side you add the hydrogen to, and the iodine is on the other side. This time adding a halogen, and rather like what we saw before, we get an addition reaction across that carbon-to-carbon double bond. In theory, you could react any of the halogens. Normally in chemistry we see with the bromine and chlorine. Reactions with iodine tend to be too unreactive. The reactions with fluorine tend to be too reactive, difficult to control. And again, we soak up that molecule, that halogen, and add it across the double bond. Halogen on each side. The only slight quirky part to the reaction is when we start with our cycloalkene. There's a very specific stereochemistry to the product. The cyclic alkenes undergoing a halogenation reaction. When the chlorines or the bromines add, they add to opposite sides of the plane of the ring. You get a trans configuration of that halogenation product. Because the reaction happens in 2 parts. One of the chlorides adds on, and when the first chlorine atom adds on, it's so big and bulky, it prevents attack by the second chlorine from the second side. Forms a barrier to further reaction on that side of the ring. So the second chlorine atom coming in, or the second bromine, if it was bromination, that second atom has to come from the underside, from the other side of the ring. Because of the restricted rotation of the ring, it locks the 2 atoms in on opposite sides. So a thicker bond showing a carbon to chlorine bond coming out of the page, and the dashed line showing the carbon to chlorine bond implying it's going into the page. So this addition reaction with a halogen, be it chlorine, or bromine, or occasional times it might be iodine or fluorine, always gives a trans configuration to the plane as a ring. If it's an open chain alkene, then there's no problem because it's free rotation. Because of the restricted rotation of the ring, they're going to be locked at opposite sides of the ring when the product forms. So it's never a cis product, with both of them on top or both of them on bottom. That never happens. Now this halogenation reaction, specifically bromine, when this reaction happens with bromine, it gives us one of our simple tests for an alkene. I mentioned this on Monday. Remember, bromine solution is a strong blood red colour. And if it attacks an alkene and adds across the double bond, if we use up our supply, the product that's produced, this dibromoalkane product, is colourless. So using up that bromine will turn the solution colourless. So the addition of an alkene to a bromine solution that turns the solution colourless is a good basic test for evidence that you've just reacted to bromine with an alkene.